Dr. Carboni?
Yeah.
Am I saying that correctly? Carboni?
Carbone, that's fine.
Carboni. Dr. Carboni. And basically at 10 after 1, we'll start the presentations. What I'd like to do is share a quick screen and read something to you. So if everybody could stand by for a moment. Okay. Welcome to the 18th Annual Summer Student Research Symposium. In virtual format this year for the first time, the symposium showcases the work of students in the Emerging Caribbean Scientists, or ECS program, which offers scholarships, summer programs, research experience, mentoring, and supplemental instruction to UVI students majoring in science, technology, engineering, and mathematics, also known as STEM. Programs within the ECS program include maximizing access to research careers, historical Black colleges and universities undergraduate program, research initiative for scientific enhancement, or RISE, summer undergraduate research experience, and summer sophomore research institute. The University of the Virgin Islands is also one of the 10 minority serving institutions for cooperative agreement awards with NASA under the Minority University Research and Education Project. The cybersecurity fellowship program at UVI has a goal to provide training and in the future increase the number and diversity of the nation's cybersecurity experts. In addition to these programs, this year's summer research is supported by the National Science Foundation, the College of Science and Math, and generous donations of private donors. At this symposium, we will have 6 sessions that are being run concurrently. You can find the schedule in the abstract book at the UVI ECS website. We will keep presentations on schedule to allow symposium attendees the opportunity to move between sessions. You can leave and enter any session as often as you like. Note that we will stick to the schedule. If a student is missing the next presentation, we'll still start at the scheduled time. So we're not going to jump the order or start someone early. If you are unfamiliar with Zoom, take a moment to familiarize yourself with its features. We ask that you remain on mute throughout the presentations and put any questions you might have in the chat box. That way the co-host can order those, and during the Q&A session, we can kind of organize that and sort that for everybody. Are there any questions from folks at this point?
Right. Tim, do you want to hold the question to the end, or during the presentations, or during after everybody?
I think if so, as I read the specifics for hosts, I think the presentations were to run between 5 and 7 minutes, which would allow 2 to 3 minutes of Q&A.
Thank you.
Let's assume, for everyone's sake, that if you take all 10 minutes, then we start off the next presentation, and we could have some Q&A time at the end, at the very end, for sessions that took all 10 minutes and did not allow a Q&A opportunity. Sound fair?
Sounds all right, but I still would like to encourage speakers to stick to their 5 to 7 minutes.
Absolutely. Yes, we do. That's the best way to handle this and to frame the opportunity. And then that way, it also means that as presenters, once you're clear for your session, you're free to drop and then join another session to witness and observe and participate in other virtual presentations. So that's why sticking to the 5 to 7 minute window, as Dr. Carboni has reemphasized, is an important idea. Okay. So I'm going to put just a placeholder here for a moment until we're ready to begin.
I had a question. Are the students able to share their screens? Because I know Princess had made some edits to her PowerPoint since it was first.
I believe they are able to share, and that's fine by me. They should be able to share. So let's see.
Yeah, they should be already allowed to share screens.
Okay, I just wanted to verify. Okay, good.
So the slide that I have received earlier, I should not queue up. Am I understanding that correctly?
For Princess's presentation, yeah, she'll probably share her screen, and she's made some edits to her.
Okay. Okay, so I'll queue up the next one then. All right, so for just a couple more moments, we'll show our handy dandy, whoops.
So Tim, do you want to introduce yourself? That's what it is.
Yeah, we can do that. I am Professor Timothy Kentop in the Computer Science Department, and my focus area is cybersecurity, but also all things computer science, all things digital, data science, and information technology. So I've been here for 4 years, and I work with Dr. Boumediene in computer science in the College of Science and Math. And I'm on the Albert A. Sheen campus on St. Croix. Dario?
Yeah, good afternoon, everyone. I am Professor Dario Carbone. I'm a professor of physics on the St. Thomas campus. And my main area of research is in astronomy and astrophysics. And in particular, I study transient sources, so sources or things in the sky that are not there every night, but are only visible at for some limited amount of time. And they're usually the most energetic events in the sky. I guess we'll hear something about what I do later on in this session.
Well, the whole idea of energetic events has the wheels turning in the back of my head. So I'm thinking of really big bangs.
Sometimes they are. All right, we have 1 minute to go. I again ask all the participants to be muted while they are attending.
And is Miss Princess Adamazam ready to share her screen?
Yes, I am ready.
Okay. Ms. Adamazam, you are clear to begin.
So I can quickly introduce Princess, even if Teresa already did it. So Princess Adamazam is a high school student who has been working with Dr. Teresa Ashcraft during the summer through the REAP program, which is especially dedicated to promising high school students. And her work is dealing with merging galaxies and how we can find them using optical telescopes. Princess, please, you have the floor.
All right, thank you. So hello, good afternoon. My name is Princess Adamazam, and yes, I am a high school student at Charlotte Amalie. And this is my presentation on searching for merging galaxies using ground and space-based telescopes. Understanding galaxies. What is a galaxy? A galaxy is a gravitational bound system of stars, dust, and dark matter. As galaxies begin as small clouds, and as these clouds get close, gravity sends these objects into another. These same galaxies can also become bigger by merging with other galaxies or even eating them. Project objective. The objective of my project was gathering information on very distinct faraway galaxies. Using images that was taken from the Large Binocular Telescope, or LBT for short, and the HST telescope, or Hubble Space Telescope, and to compare the resolutions viewed with these galaxies from the different telescopes. The reason I used 2 different telescopes because they wouldn't have the same resolutions, and what I could see in one, I wouldn't see in the next. This project was important because it helped show the matter in the universe, how it is organized, and how it has changed throughout cosmic time. Distant galaxies, wavelengths, and redshifts. How I managed to see these images was using software such as DS9, which helped to properly view these galaxies and observe features. I've also been using the NASA Extragalactic Database, or NED for short, to research these images I have found. Basically, how NED works is I would get the coordinates, the lines of declination and right ascension, and place them in a search location box. With these coordinates, it will load various images located around that area. I tend to follow with the closest to exact coordinate. Now I have the image that I found on DS9, and I look at the information found on that object, such as its redshift, what type of object it is, any references, and what spectral region it was detected in. Types of galaxies. There are many different galaxies, and there are a few I learned about. These images were from the Gems and Goods field paper that I've read to gather more information. Figure 1 shows the Star Wars tidal tails, the color images, and these properties of tidal tails is used to understand the interactions between these galaxies. Figure 2 shows the attendant galaxies, which had long structured arms. And figure 3, the M51 tidal tails, these images look way darker than the rest, and it's more difficult to see contrast between galaxy and stars. Merging galaxies. In this image, taken from the LBT, there are three objects. The first is a merging system, and you can tell by the 2 structured arms and the 2 heads. What I wanted to figure out is if the object below was also a merging system. In order to know if a system is merging or not, they must have the same redshift. Looking at this image, I was sure that it was a merging system. Then doing the research on NED, these 2 objects had 2 different redshifts, which conclude it was not a merging system, but just a line of sight. When I first looked at this object from the LBT R-band, I didn't think there was anything going on. Then when I compared it to the HST 814, I noticed that this could be a merging system. This is why it is always good to use different telescopes and filters due to them giving different resolutions so you can see each object better. And the difference between the LBT and the HST is the LBT is inland and the HST is in space. So the HST doesn't have to worry about getting black from our atmosphere and giving off different resolution. I looked for these objects on DS9 where I got a hit. They had the same redshift. In the image, Z represents redshift. So these 2 objects had the same redshift of 0.189, which would conclude it was a merging system. Overall, this was one of my favorite objects thus far and got really excited when doing a background check on it. Summary. Overall, in search of galaxy interactions and mergers in this project, I have found about 25 examples on the software DS9 from the Large Binocular Telescope U-band and with the help of other filters. With these images, I obtained information on what type of object it is and identify if it was merging or on the verge to merge. I created a chart of these objects with information, with descriptions, and along with guided information from NED and other research papers. Thank you.
Thank you, Princess. Very nice presentation, and I'll open the floor. If there are any questions, please unmute yourself and say your name and ask your question. We have a few minutes.
Good afternoon, this is Professor Kentop. I would like to ask Ms. Princess if she could email us the updated copy of her slides, just so that we have what was presented. That's all. Thank you.
Other questions? I have a question if nobody else. So you have talked about in NED, especially the catalog from NASA, that one of the entries that you have is I think you called it like spectral band, So
Yes.
do you mean that that is the band, usually optical, in which the galaxy was discovered? Or like for like galaxies that have observations in different bands, you have all the data recorded in there for different bands?
Yes, wherever the galaxy was detected in, it was shown under the spectral region. Sometimes I would have some detected in the radio, sometimes I would have some detected in the X-ray, sometimes I would have some detectable in the visible IR. Different galaxies were detected in different spectral regions.
Thank you. Other questions?
Yeah, I have a brief question if we have a couple more minutes. This is Professor Morris. I also, for those of you who don't know me, I'm also a faculty here on the St. Thomas campus at UVI, teaching in the physics program along with Professor Carbone. So a quick question. You're talking a lot about these merging galaxies. And can you just tell us a little bit about, if you've done this much reading into merging galaxies, what's going to happen to these galaxies after they, all the ones you showed seem to be sort of just beginning their interactions. They all kind of look at like they're, just beginning to collide with one another. So what, would you expect, if you're able to come back and view these galaxies, millions or hundreds of millions of years from now, what do you think might be the outcome of these interactions? What happens when these galaxies finish their merger?
Can you repeat? I couldn't quite hear you.
Yeah, so can you tell us a little bit, if you've talked about this, over the course of your internship? I'm just wondering if you could tell us a little bit about what's going to happen once these galaxies finish their collision. You found some that were just chance alignments, weren't really colliding. Then you showed us one at the end there with the, I think the LBT and the HST data that we think actually is colliding. So what's going to happen once they collide? What's sort of the next stage of that interaction?
I didn't really quite go forward to what's going to happen after they collide. I know instead of two objects, there's going to have one main galaxy.
Yep.
But
Yeah, that's exactly right, Princess. Remember those videos you watched?
Mm-hmm.
Yeah.
Okay, yeah, that's great. And one of the reasons I asked is just kind of big picture kinds of stuff, right? Some of you guys may be aware that this same sort of fate is waiting for the Milky Way galaxy, our own galaxy, right? Many years from now. But we're on a collision course with the Andromeda galaxy, which is nearby us. So these kinds of, there are many reasons to be interested in studying merging galaxies. They tell us a lot about star formation and the way that galaxies evolve. But it also may be personally interesting to our own galaxy a long time from now, because we're going to do that very thing in the distant future with Andromeda. But great presentation. Thank you, Princess.
Thank you.
Thank you again, Princess. It's time to move to the next presentation. We are spot on with the time, so we can stop sharing Princess' screen. And the next presenter is Derek Thomas. So we can upload, we can share the screen with his slides.
Well, actually, could I share my screen instead?
I don't have a problem if you share your screen.
Okay, just I did also, I sent the wrong file. So this one has the correct information.
Okay, please begin.
So yeah, Derek worked as well with Dr. Teresa Ashcraft. This time, Derek is a student at UVI, and his research is within the ECS program. Go ahead, Derek.
Okay, so good afternoon, everyone. I'll be presenting Investigating Merging Galaxies. This is my work with Dr. Teresa Ashcraft at the University of the Virgin Islands under the NASA Miro Award. And now I will continue my presentation. So about what we did for our research, this research focused mainly on studying the merging of galaxies and understanding this phenomena. And within our research, we were trying to look for these galaxy mergers using images taken from the Large Binocular Telescope and the Hubble Space Telescope. And the reason for these two different telescopes is because while one is land-based, the Large Binocular Telescope, which is in Arizona, the Hubble Space Telescope is, well, in space. And that allows for much clearer images because it is outside of our atmosphere, and our atmosphere usually distorts images taken in space. So it's a good idea to combine these two images from these telescopes and compare them and see which gives us the better view. So in my side of the research, as you've heard from Princess before, she looked into figuring out these mergers and identifying them from images. On my side of things, I went and tried to work on creating a code to help identify these images autonomously. And I'll talk more about that code later on in my presentation. But overall, our goal was for myself and Dr. Ashar, was to create this program to identify these properties of galaxy mergers and these images taken from these telescopes. And in a way, we were able to compare them and find things that will be able to compare between each of these mergers, that will be able to identify them faster and be used in this code. So a little bit of background on merging galaxies. When this happened is when two galaxies have begun to merge because of their gravitational pull towards each other. And you can see in this image right here, the antenna galaxy. One way of ideally finding a galaxy merger is to look at these two what we call tidal tails, which are sticking out from these galaxies, which help us identify these galaxies within images that are taken. And these are important find, which helps us identify what we're looking for quickly. And underneath, you can see where this picture is taken from. So ways of finding our data was that we used images taken from both of these telescopes, which are shown below. And these telescopes are able to take hundreds of images, which are then rendered into programs such as DS9 and so on, that allows us to look at these images. And usually these images are seen on a gray scale, and that'll be explained more later on in the presentation. And using these images, these images provided are taken from extragalactic deep fields, which is shown that these are areas which you are able to view multiple galaxies outside of our own. So that's why we need a combination of both telescopes in order to see these extragalactic deep fields. So more what extragalactic deep field is, it'll be an area which are seen outside of our galaxy, which allows us to see all of these multiple galaxies. Now, everything that you see here, these aren't stars, these are all galaxies by themselves. Each and every dot and color that you see is a galaxy. And usually these galaxies are seen, as I said earlier, in grayscale, which is normal for how we identify these galaxies, because that is how a better view of what it is when you actually look at them outside in space. And these colors that we have here are what we reimagine these images to be, and using different filters that are color filters that are detected from these galaxies, we're able to create these colors, which are able to give a better representation of these galaxies. So this right here is an example of a merging system when two galaxies are coming together. And this is the image that I identified myself using DS9 program. And here you can see the tidal tails that I mentioned before, which is a good indicator that these galaxies are indeed merging. And so onto what I did throughout the summer, which working with the Python code. What exactly the Python code would do is reading data about regions within these images. And from there, we can compare these images of possible galaxy mergers, and we'll see which merger is possible and which isn't. And we'll be able to see if they have any common properties. And from there, we'll be able to decide that this is what the code should look for within these images. And in that way, it become a lot more autonomous in finding these images, because when these galaxies take these images, it's hundreds of images, and that could take hours for scientists to look through and identify. But if you have an autonomous system, we could take what would take hours and put it into minutes, which would greatly increase data find and also maximize the amount of time needed for these research possibilities. So that is what we're focusing right now on Python coding. So from results and conclusion of our research this summer, we were able to find potential galaxy mergers within the images that was given to me by my mentor. And from there, we were thinking of a method on how to possibly identify and graph these occurrences through the code that will allow us to find these mergers a lot faster. And we concluded that mergers may possibly have similar properties that we could categorize and use them within the code, and that way the code will be able to find them faster for other images that may be input into the code. So in that way, things would be a lot more autonomous and faster, and a lot more images could be go through, and we'll be able to find more phenomena. And so in the future, we'll continue to try and work on testing out these codes using other programs as well as AstroPy and Source Extractor, and try to find a way to combine these programs with the code and create a way to find these mergers that we're looking for. And of course, this research is possible from my mentor, Dr. Teresa Ashcraft, the NASA MUVET Award, and of course, the physics department. And thank you very much for listening to my presentation. Any questions?
Thank you, Derek. We have 1 minute, so if we have one quick question, that can be taken.
Just to clarify, this is, so they want to.
Okay, I will ask my question then. What is the output of your script? Is it just a list of coordinates where to look at?
That is ideally what we're thinking of, because you can, in DS9, you can see the coordinates of whatever region that you're looking at. So from there, you'll be able to look at the properties from the headers of these regions and see that, okay, this region shares the properties that we're looking for. So then it'll look at the coordinates and it'll output these coordinates towards you. So that's still along the lines of what we're thinking of. So that we'll be able to, instead of having to physically look for these regions and put down these coordinates, you're able to find these coordinates. The code will give you these coordinates and you know where to look, and make things a lot easier and faster.
Okay, good.
So
Thank you very much.
I don't have a question. Dario,
I think
if I can get a really quick comment.
Due to time, I think we should move to the next speaker. We are already slightly over time.
Okay, sure, go ahead.
Sorry, David.
Okay, I guess I'll talk to you another time, Dr. Morris.
Yeah.
Yep, sounds good.
Thank you again. Derek will move to the next speaker, who is Michael Dow. So we can pull up his slides.
I have your slides ready to go, Michael. Are you ready?
Yes, I'm ready.
Okay. Share screen.
So Michael, you should tell when we need to go to the next slide, of course.
All right. Good afternoon, everyone. My name is Michael Dow Jr., and I'm a upcoming sophomore on the UVI St. Thomas campus. My mentor is Dr. Antonino Cucchiara, and the project we're working on is algorithm optimization for fast transient identification of deeper, wider, faster data. Next slide. So the Deeper, Wider, Faster program, or DWF, includes over 40 different astronomical observatories, both land-based and space-based, which simultaneously observe a much wider area of the sky than would be possible with a single telescope. Some of these facilities include the Swift Telescope, as well as the Etelman Observatory in St. Thomas, as well as many others. These observatories conduct observations on a large portion of the electromagnetic spectrum, including infrared light and gamma rays. And the survey focuses on the detection of fast transients, specifically counterparts to fast radio bursts or FRBs. Next slide. Very fast transients are astronomical objects whose brightness drastically increase and decrease over a short period of time. Such objects include FRBs, as mentioned before, gamma ray bursts, and supernova. And these events can last anytime between a few hours to just a few milliseconds. Next slide. Now a little bit about why we're doing the work we're doing. Supernova are fundamental to understanding the catastrophic ends of stars 10 times larger than our sun. Gamma ray bursts may be the only objects that can help us understand the first stars ever born in the universe. And fast radio bursts have only been discovered relatively recently, and their origins are still unknown. Next slide. So what our project is doing is creating an algorithm that will go through the data gathered from the DWF survey. And these are two of the light curves I was able to develop when I first started. They both give the magnitude of the star's brightness, and in astronomy, the smaller value is a greater brightness. And it also gives a time value in the modified Julian date, which is essentially the number of days since midnight on a date in November 1858, I believe. Next slide. So what I've been able to do so far is write a Python program that can read data from a DWF file. It plots the brightness versus time. It's able to convert the modified Julian date into values such as seconds, and it can also be changed to minutes if necessary. And it creates a model for decaying light curves so far. The model is also able to determine the decay index alpha, which tells you how fast these objects eventually disappear. So the graphic I have here is like a before and after. The graphic on top is when I first started. It shows the magnitude, showing the smallest value going down to the larger value, and it gives the time values in the modified Julian date format. Now where I currently am, it converts the modified Julian dates into seconds, and the label tells you when it started. It also shows a model, decaying model to match the data, and it displays the decay index. Next slide. So as I'm going to continue working on the project, the next steps include working towards an algorithm that can run simultaneously with the DWF survey on a supercomputer and extract the light curves of objects of interest. As mentioned before, these are gamma ray bursts and fast radio bursts. The program will be able to create models for all light curves with no inflection point that's decaying and increasing, and extract the parameters from the model, which is the decay index and accuracy of the model. Then the program will be able to select the fastest decaying objects, which are most likely to be GRBs, FRBs, or other unknown sources we have not identified. Next slide. Thank you. Any questions?
Okay, thank you, Michael. We have time for a couple of questions. I'll ask the first question then. So if we can bring up the slides again, please. You have talked about your script should be it creates these fits, which in the case that you have shown was an exponential fit. But how does is the fit done within the program, or are you taking the best fit from somewhere else? And how is this done? Can you elaborate a little bit?
So what Dr. Kuchar and I did was we created a function in Python, both a linear function to fit data sets that are more similar to a linear graph, and a function that's an exponential decay function. So right now, based on how the data looks when we initially plot it, we choose which function would best fit it, and then the program automatically creates a model for functions similar to it.
So there is one thing that Michael said in one of the last slides, was that he was talking about figure decay, like the one that you see there, going down, right? You look at both plots as the same data, right? So the brightness starts and then it continuously decaying. So that's one example. In one of the earliest, the other options that you have an object that becomes suddenly brighter and then fainter. Like this case, you can see the bottom points, you have a lot of up and downs. So we are looking for implement this code. As Michael said, he implemented a function for a linear, like a straight line, an exponential decay. Then we're going to try a couple of more, like a parabola shape or some sort of like peaky function in some way. The idea is that the code recognizes automatically what type of light curve it is. Is it a straight, is something that goes, that decays only, or becomes bright and then decays? We call it an inflection point. He mentioned in one of his bullet points at the end. And the next implementation of Michael's work will be telling the code, if you do not see any inflection point, which is like the graph on the left here, then you can use either the power law, the linear function, or the parabola, and then it'll produce some goodness of fit, right? Choose which one of the three models is best. Instead, if he sees an inflection point, meaning it becomes brighter and then fainter, or fainter and then brighter, then we'll use a different function, like a parabola or something like that. So that's where we are at the moment with the code, Michael. But the idea is that everything has to be done. Right now, as Michael said, we look at the graph and we decide what to fit. So the idea is that the code will do it on its own.
Okay. Thank you. And we can move to the next speaker, who is Joshua Paris. So we can put his slides on. And Joshua is a UVI student who's been working with myself during this summer on detecting radio transients. And Joshua, you have the floor.
All right, good afternoon, everyone. My name is Joshua Paris. As Dr. Dario Carbon explained, I worked with him this summer for the ECS program, working on detecting radio transients. So, yeah, next slide, please. All right, so, so transient sources they are not constant. They're not always there in the sky. So in other terms, they are, I forget the words. They are impermanent. So that was, yeah, transient sources are impermanent. And in order to tell whether a source is transient or not, you will need to measure the flux of these sources multiple times in order to see how it evolves over time. And also, you have to put into account the noise of these transient sources, And noise isn't that you will hear in a car or hear a dog barking. Noise is something that affects the true measurement of what the flux is for these sources. And among the and for the sources that we'll be focusing on would be transient sources that are visible using radio waves, which give them the name transient sources. So next slide, please. So the reason why we want to study these transient sources is because the rate of these sources they are important, but they are not very well. The rate of them is not very well constrained. And what I mean by the rate is how many of these transient events happen over time. So we want to be able to put a rate of them. That was our main goal for this project. Next slide, please. So the methods we use a telescope. We use a radio telescope called LOFAR that had images. And with those radio images, we use a computer program called DS9 that allows you to look at the parameters, the coordinates of the transient sources on the radio images that was taken from the sky. And also we use computer language called Python. Python allows you to create the light curves that will allow you to tell whether the source is transient or not, and helps you create plot graphs. Yeah. Next slide, please. So here, we had the images, we put them into 4 different fields, and we only focus on 4 sources in the first field. So these are the light curves that we created using Python. And these are the 4 sources here. So based on the light curves, from someone who's not sure what they're looking at, you could say that these plots are all over the place, so you can't really tell if this source is constant or not because it doesn't have a constant plot. So we created the line of best fit, and the numbers to the side of the sources are the numbers that we got from the line of best fit. So once the number is close to 0, allows you to tell that this source you're looking at is not transient. It's very much constant. So despite how the light curves looks, the number is further verified that these sources that we looked at are not transient. Next slide, please. So the challenges that I faced over the summer were getting used to Python. Python, I never had any background in using any computer programming language or programming as a whole. I never had any background in it. So this summer, it helped me overcome that challenge of getting used to what programming is and stuff like that. And also grasping the new information about radio astronomy. I had no idea what radio astronomy is. I didn't know that it even existed. But this summer I got to learn new information, and it brought in my mind about how transient sources work and different components of space. Next slide, please. So these are my results. So my results, excuse me, as I said before, the transient source, there were no transient sources found. So we decided to put a rate on the sources that were found. I mean, to limit the sources that were found. So in order to do that, we use a method described in Carbon et al. 2016. And that method, it gives you the upper limit of the transient surface density of these sources. And how we got that, we assume that all the images have the same field of view, and that they are from the same part of the sky. And we also found the pairs of those images, the possible pairs for those images, and we got that data and came up with a limit to put on those numbers. So the limit that we could put on those numbers were 2.5 Janskys, and that determines the sensitivity of the noise. So that was the limit that we could have put on those numbers. And that's the end of my presentation. Oh, yeah, this is the end of my presentation. Anyone have any questions?
Thank you, Joshua, for your presentation. We have a couple of minutes for one question.
Yeah, I'll ask a quick question. So, Joshua, can you go back to your light curves plot? So can you just explain to me a little bit in these light curves? So you have, multiple dots, multiple data points that look kind of like they're sitting at the same X location. As an example, your upper left plot, right? The one in the upper left corner, you've got 1, 2, 3, 4, 5, 6, 7 dots over there at 0 days. So can you just, and the same repeats, right? You got multiple dots at these different, day points. So can you just tell me a little bit how to interpret those dots? Are they really lying on top of one another, or are they just separated by so small an amount that I can't see the horizontal separation? So what's going on with those data points?
Okay, those data points together because the fluxes of those sources were very similar in multiple pictures. Also, the pictures they were taken, some of the pictures that we looked at were taken one couple minutes after the other. So that's how come they are so clustered together.
Okay, so they're not really on top of one another. They're very close in time.
Yeah, very close in time and fluxes.
Okay, great. So I guess you're telling me that for all of these plots, they pretty much are consistent with no change over that whole 175 days. I think was that the takeaway? That's what those numbers near 0 in the title tell me. Is that correct?
Yes.
Okay, great. Thank you.
Yeah, thank you very much, Joshua. And we move forward to the next presenter, who is Joel Mwabungu. You can put up his slides. He has worked on his project with Dr. Morris here at UVI and with Dr. Nikolic and Dr. Oyake at JPL. Joel, you have the floor.
Good afternoon, lecturers, students, guests. My name is Joel Mwabungu. I'm a third-year physics student at the University of the Virgin Islands, and I'm here to present to you my internship project that I did over the course of the summer with Dr. Morris, Dr. David Morris, Dr. Nikolic, Dragan Nikolic, and Amali Oyake. And I did this in conjunction with the University of the Virgin Islands and the Jet Propulsion Laboratory. So next slide, please. So let me preference my presentation by giving some background information. What I'm doing is the automatic detection and analysis of signals. And this is going to be done in conjunction with the overall UVI CubeSat project. So a CubeSat is just a miniature nanosatellite, which is going to be launched into space, which is launched into space now, but UVI is developing one, and it's going to be aimed at detecting gamma ray bursts. And a gamma ray burst is just a short-lived burst of light, very, very energetic explosion in the sky. And like all machines, these gamma ray bursts and all phenomena in nature produce signals. So what I'm doing is just creating a framework in the back end to develop these, to detect these signals. And this framework is going to be developed in a 3-stage process. The first is that I'm gonna obtain some data from Dr. Nikolic at JPL. The second is that I'm gonna redact the data and then create algorithms and software in order to read in this data and produce output signals. And I'm gonna be finding algorithms to detect the height peaks in addition to the time that these peaks occur. And finally, I'm gonna be using a custom scientific instrument called the Redpetile to generate my own custom signals and see if my own program can detect it. Next slide, please. So these are some images. On the upper left-hand corner, you can see a gamma ray burst. On the upper right-hand corner, that's a CubeSat. And on the lower left-hand corner, that's the Redpetile board that I'm gonna be using to generate automatic signals. So next slide, please. Time to explain to you what I did. The first step, as I mentioned to you, was that I obtained a data set from Dr. Nikolic, who works at JPL. And this data set was from the International Space Station, specifically a spectrometer. And this spectrometer had output signal data. So my first step was actually to redact the data in conjunction with Dr. Morris and Mr. Oyake at JPL. And then the next step was to produce algorithms and Python scripts in order to read this data into a computer. And then afterwards, I had to generate custom computer programs to detect the peaks present on this data, and also identify the highest peaks, all the peaks present on the data, as well as the height and the time that all these peaks occur. So after that, I need to use the Redpetile to generate custom wave signals using another tool called MATLAB. And I'll be creating an algorithm in MATLAB to generate the wave signal. And once that's been generated, my own program is going to be able to detect the peak. So next slide, please. And what you can see on the left-hand side is an example of one of the output data signals, which was generated. So that, what you're seeing on the left-hand side is just a standard wave signal, which was detected using the algorithm. And what you can see on the right-hand side is an enhanced view of that, but this one is more so of all the peaks present. And to give you some additional information on this particular topic, well, go to the next slide. Let me try to speak from there. So the algorithm was created to be able to detect peaks, but what I'm doing is not reinventing the wheel. So there's several different people and engineers, researchers who have already developed algorithms to be able to do this. But what I've been having some trouble doing is that the shape of that plot that you saw in the previous slide is unique. And it's for our own purposes, the purposes that from the data that was provided to me. So even though there are other algorithms which are capable of doing this, I needed to create my own algorithm because those don't work with my particular data set. So that was a major issue that I encountered. In addition, the algorithm was too sensitive. So it would detect signals, it would detect any bump that was on the signal plot and classify that as a peak. So I needed to create another algorithm to be able to desensitize it, which I did. And the last step of this project is going to be using the Redpetile instrument to generate my own signals and classify it. And the future work includes using this own algorithm and this software to be able to hook it up to the instrument present in UVI's lab to be able to continue the work of the CubeSat project. And finally, I would like to add some features, including front-end capabilities to my program and my software. Next slide, please. And finally, I would like to thank the University of the Virgin Islands Physics Department, the Jet Propulsion Laboratory, Dr. David Morris, Dr. Dragan Nikolic, Dr. Amala Oyake, the University of the Virgin Islands grant this number, in addition to Ms. Orfa Penn, who provided me with my MATLAB lessons. And I would like to show you my programs, but I've been told that's not a good idea. And I would like to thank you guys for listening to me. And I would like to open the floor to any questions. Thank you.
Thank you very much, Joel. We have a few minutes for a question or two at most. And in the meanwhile, if you, I do not see Jordina here, so if you can contact her, please do so because she's next.
Okay, I'll do that right now. But
So, any questions for Joel?
I have a question.
yeah,
You
shoot.
said you used, my bad.
Yeah, you good, Ax? Sorry. Yeah.
You said you used MATLAB.
Right.
So is DS9 also applicable to your study?
No, I didn't use that particular application. What I've been doing is using the Red Pataya proprietary software. So these are programs already created by the Red Pataya parent company, and they created it already for all the users across the world to use. So I just go into their website and they provided the program to me, and I just had to change the arguments and the parameters so I could use it MATLAB. But I haven't used DS9 though.
Okay. We have time for one more question. If nobody has one, let me ask a very naive one.
Yeah.
When do you think or do you hope our CubeSat will launch?
Well, I don't want to put anybody on the spot, but I don't make anybody grand assumptions, but I think the next year and a half, UVI hired 2 engineers so that they're going to be working on creating the electronic capabilities of the CubeSat. In addition, we're going to be continuing to work with the engineers and the researchers at JPL. And this project actually isn't finished, so it's a full-time thing. So I'm going to be continuing to develop the capabilities of it. So if we all work really, really hard, I'm assuming it's going to be in the next year and a half.
Yeah, I'll add quickly to that if I can. So Joel's got the timeline right of a year and a half, but the deliverable in a year and a half is the prototype for that CubeSat, and the first step in demonstrating the capability is to put it onto what we call a high altitude balloon flight. That'll go up to 100,000 feet and basically spend a day at 100,000 feet and collect data. And then that returns, we take that off and then we modify. It's basically the same package that we then kind of repackage, put on the CubeSat. And then we just basically wait for a ride in a rocket. And that likely will take probably another year after that. So year and a half to the balloon flight and probably another year until we get it up actually into orbit.
Thank you very much. Thank you again, Joel.
Thank you. Appreciate it.
Up next is Jordina Pierre, but I do not see her in the Zoom room. Please, Jordina, if you are there and I'm missing you, please forgive me first and speak up. I do not see her. So in order to keep the timeline order to what we have, I guess we can give her a few minutes. Whenever she joins, she will have less than 10 minutes, I guess. I think I saw her popping in and out of the room.
Dario, why don't we move on with the schedule and eventually she get the 10 minutes after at the end, whenever she gets in?
Well, the thing is that what we were instructed to do was not to do it.
Really? Okay.
Because people who want to attend, say, for example, Celine's talk, who's up next, they would tune in at 10 past the hour and they would have already missed her talk.
I see.
She hasn't provided as recorded slides.
I'm not sure. Tim, can you put up her slides?
Did. I'm about to pull those up now.
The thing is that even if that was the case, she should have been present. That's anyway, we can give it a try. don't know if this is a record. I don't think this is a recording.
Derek, you have her phone number. Why don't you give her a shout out and see if she can join us?
We are seeing the slides from Jordina Pierre, but she's not here yet. So some of you wrote to me, like you cannot hear the presenter. That's because the presenter is not talking.
So I think Jordina has said that she joined, but she wasn't able to. She saw that you're sharing, Tim.
Hi, can you hear me?
Yep, we can hear you, Jordina.
I sent a pre-recorded presentation to I can't remember her name, Verlene. Yes, Verlene.
Okay, we did not receive that file. We only received what it's being shared on the screen now. When I say we, I mean myself and Dr. Kento, who are the moderator of this room.
Because currently I'm at work right now, so that's why I sent the pre-recording so that it could play.
Well, I guess we can play it at the end of the session. Now it's a bit too late, but we should first of all get, if you, Jordina, can send an email to Verlene and tell him to share the recorded presentation with myself and Dr. Kentop, that would be nice, because I don't know where to look for it.
Okay, I'll email her right now, because she responded to me and she said she's replacing what I sent yesterday with the recording. So you want me to just tell her, or would you like me to include you in the email that I sent her?
If you can include me, it would be nice. Thank you.
Can I have your email, please? Because I don't think I have it on this email as yet.
Are you asking for my email or for Verlene?
Yeah. I have Verlene's on. I sent it last night.
Okay.
And Renata Plantenberg.
Yeah, my email is my name dot my surname at uvi.edu.
Jordina, don't worry. We'll check with her and we'll find the presentation. If you send it to her, don't worry. Just you are at work. We'll figure it out. Okay. So we'll go from here and let you know. Okay.
Okay. Thank you so much.
Well, okay. We'll figure this out later on, but now we can start moving on. The next presenter is Celine Prentice. She has worked with Dr. Saf here at UVI and with Dr. Ramsey at the University of Virginia, and she's going to present her results today. Celine, you have the floor.
Hello, good afternoon. My name is Celine. I am a senior at the University of the Virgin Islands studying physics and math. And today I will be talking about my summer research entitled Producing Synthetic Observation of Dust Emission, but the producing part got cut off. Okay, so in astronomy, outer space is our laboratory. Unlike a typical lab, we have no control over what we are examining and instead resort to creating computer models to understand what we see with telescopes. This is also true for star formation. We can observe them, but we need models to understand and learn about the underlying physics. Yeah. When stars are very young and are in early stages of formation, they are called a protostar. As they evolve and accumulate mass from the circumstellar disk, they produce protostellar outflows. Protostellar outflows are caused, oh, you could go back to the side. Yeah, that's fine. Protostellar outflows are caused by gas and dust that never reach the young star. They instead interact with a dusty envelope and is ejected perpendicularly into space, as seen in this image. The objective of my research is to produce a synthetic observation of a protostellar dust outflow at different masses in its evolution. Next slide. To produce this synthetic image, we have to plug in the density at various stages, as shown by the blue box, into a 3D imaging software to calculate the dust temperature, the orange. Next slide. These images represent the magnetic field and densities from Staff et al. 2019 for each stage in this star's evolution. RadMC 3D is the 3D imaging software used, and because processing the data is memory intensive, a supercomputer is required. Using densities taken from Staff et al. 2019, RadMC 3D, and other Python plotting libraries, the dust temperatures were calculated and the first stages of images were produced for the young stellar object at 1 solar mass. Next slide. These series of images include the position in relationship to the density. Next slide. Temperature. Next slide. Different wavelengths and inclinations. These are maps of the intensity. These are maps of the intensity of the dust emission in different wavelengths, and essentially the goal of my research. Next slide. Because my research is currently ongoing, future work entails finalizing the images for a 2, 4, 8, 16, and 24 solar masses and showing the relationship between the way light interacts with dust in each wavelength. Many factors, distance from Earth, and atmospheric interactions, to name a few, impact what we observe with a telescope. Concluding this research includes implementing those variables using CASA. Towards this goal, images at wavelengths relevant to ALMA and the Very Large Telescope will also be produced. Next slide. The next slide is just my acknowledgements. Partially, it's just the grant number, and that is all for me.
Thank you very much, Celine. We have this time plenty of time for questions. So please ask your questions if you have any. Okay, then I have a question. Can you please go back a couple of slides? Okay, no, a bit further. when we had the plots, yeah, the other way. Yeah, go ahead. Go ahead. So can you please give a little bit more instruction of what we are looking at here? What is represented here? I guess what we see is a disk. That's why we have a narrow band at the center, but can you please elaborate a bit more on what we are looking at here?
Yes. So this is essentially the picture that we saw in my introduction, but from a different angle. And also we now know that this is the 1 solar mass. So this image was calculated using those parameters for that particular mass from Dr. Staff's data. And so what you see is the Y, you can't see my pointer, but so what you're seeing is looking at it from a 90-degree angle. So you're basically seeing the stream. This is the outflow that you are looking at. In terms of temperature.
Yeah, where's the protostar?
It would be at 0, like 0 Y.
Right,
Which
at
would
0
be
Z
the middle.
also. Right.
Yeah.
And the outflow is then going which way?
I guess the right in this case.
Correct.
There's time for one more question.
right, Morris.
Okay, if there are no further questions, then thank you, Celine. And we can start putting up the slides for the next speaker, who is Kahim Walter. And Kahim, wait a couple of minutes because we're going to start at 20 past anyway. Actually, I do not see, is Kahim here? He definitely was.
He said he had to restart his computer, so he's coming back.
Okay. Okay, I guess Kahim is here.
Good day, everyone. Can you all hear me?
Yes, we do, Kahim. You're good.
Yeah. Is it fine if I go ahead and start?
Yeah, you should wait 1 minute, but that I think we can go ahead. So Kahim Walters is a UVI student, and during this summer he has been working with Dr. Morris on the UVI GREAT project. So go ahead, Kahim. You have the floor.
Okay. Good day, everyone. My name is Kahim Walters, and my project for the summer was working on a requirement traceability matrix document for the UVI GREAT. And before I get started on the requirement traceability matrix document, I'll give a little bit of background on the UVI GREAT mission. Next slide. Okay, so UVI GREAT stands for University of the Virgin Islands Gamma Ray Experiment for Astrophysical Transients. And the first mission for UVI GREAT, which the requirement traceability matrix document is on, will be a gamma ray detection instrument to monitor gamma ray sky for transient sources. This instrument will be launched into the upper atmosphere at about 100,000 feet using the High Altitude Student Platform Balloon Program, also known as a HASP, which I'll go over a little bit on the next slide. With the success of this mission, UVI GREAT, the next mission for UVI GREAT will be to be constructed as a 3U CubeSat, and it will complement NASA Burst Cube and Fermi Gamma Ray Observatory in the detection of gamma ray bursts and enabling a near complete sky coverage by providing 2 pi field of view. In the image on the right, I have hardware similar to what we'll be using on the UVI GREAT. On the left is a SIPM array mounted on a triad board and a cesium iodide silicon crystal. And these hardware will be used to be able to detect the gamma rays and give a readout. Next slide. Okay, so the High Altitude Student Platform is a Louisiana State University program, balloon program, and it launches every year, carrying up to 12 student design and build experiments. There's a few example images on the right. Next slide. Okay, so gamma rays are high energy, short wavelength forms of light. And the gamma rays we'll be interested in, well, not for this particular mission, but for the next step in UVI GREAT will be gamma ray bursts that I mentioned earlier. And there are 2 versions of gamma ray bursts, short gamma ray bursts and long gamma ray bursts. Short gamma ray bursts last less than 2 seconds, and long gamma ray bursts range between 2 seconds to a few hundred seconds. And the type of gamma ray bursts we'll be interested in will be short gamma ray bursts because they're correlated with gravitational waves. Next slide. Okay, so the requirement traceability matrix document is a systems engineering design document that kind of demonstrates how the top science objectives of the mission correlate and relate to the subsystems and the more detailed system level and component level requirements. And it makes sure we understand the flow of project and the downstream impact of upstream design decisions, along with informing project management decisions regarding component purchases, assembly techniques, and verification and testing practices. Next slide. So the requirement in each subsystem, like I was mentioning before, is dependent on the primary science objective. And these objectives should be traced back to our main science objectives or goals and mission requirements. So what this means is the top level science requirement of this project per se is to detect transient gamma ray sources. So the subsystems, which include structures, electrical power, command and data handling, the requirements for each of those subsystems should be traceable back to one of the top level science objectives or science goals or mission requirements. Next slide. Okay, here's a screenshot of what the requirement traceability matrix looks like. In this screenshot, I included the goal objectives and the mission requirements. So on the far left column, you have the ID of the requirement, and to the right of it is the requirement statement itself. So as you can see, if you read mission 2 requirement, it says mission shall produce time resolved light curves of 0.1 seconds bin continuous data. The column to the right of that requirement is the traceability column, and it traces back to goal objective 2, which is distinguish GRBs from persistent sources. And the verification for that requirement would be simulations and physical testing with our equipment. So the document just shows the relationship between each sub-level, each subsystem requirement and how it traces back up to the top level. Next slide. Okay, so future work. The requirement traceability matrix isn't complete. As you saw in the previous slide, there was a little red note that said we have to quantify our energy levels. So there are certain things that we need to go into a lab and complete in order to have a complete requirement traceability matrix document. And there are also, while we're working on the UVI grade mission itself, we may run into a few hiccups or things that need to be fixed, and requirements will be added after we establish those problems. And that's the end of the presentation.
Thank you, Kahim. We have time for a few questions.
I have a question for Kahim. So is this document what we say like a living document, like it's going to be open and modifiable until the end of the project, or there is a time where you say we have it done and that's what we're going to follow for the next phases of the development?
I think it'll be an open living document, because like I said, when we start to go back into the labs and start working on the mission, there'll be a few things that we notice in lab that we need to fix or need a requirement for. So throughout the process of working on it, I know we'll have to add a few requirements, but I'm not sure if there'll be like a ultimate deadline where we say, okay, after this point, we won't be able to add anything else, or we should stop adding things after a certain time limit.
Thanks.
We have time for one more question. If we do not, then I have one question for you, Kahim. You mentioned that one of the requirements is to be able to distinguish gamma ray bursts from persistent constant sources. Are you planning also to do something like distinguish gamma ray bursts from any other type of gamma ray event?
This particular mission on the HASP, we won't be particularly looking at gamma ray bursts. We'll kind of be looking at persistent gamma ray sources like the Crab pulsar. We'll be lucky if we detect a gamma ray burst, but that's not the main objective. So we'll just be focusing on persistent gamma ray sources.
Yeah, I'll just follow up quickly on what Kahim said. Everything Kahim said is absolutely right. The ultimate goal is to have this be a longer-lived mission. This short balloon flight is sort of a testing of the algorithms that will write for doing this distinguishing. So we certainly want to be able to distinguish between persistent and transient sources based on just their, brightness levels and basically their light curves. But we'll also have some spectral resolution capability as well. So we'll be able to distinguish the kinds of sources based also on, their peak energy and spectral shape and things like that as well. Some limited ability there.
Yeah, cool. Thank you very much. And thank you again, Kahim. Very nice presentation. We move on to the next speaker, who is Stephanie Bullock. She is right here, and we can pull up her slides. Thank you. Stephanie has been working with Dr. Torgerson and Dr. Oyai at the NASA JPL. So, Stephanie, go ahead. You have the floor.
All right. Good afternoon, everyone. My name is Stephanie Bullock, and I am a biology and physics major at the University of the Virgin Islands. So today I will be presenting on my research project that I've been working on with the NASA Jet Propulsion Laboratory and the California Institute of Technology, and it's entitled Management of Sensor Networks. This summer and previous summers, I've been working with Lee Torgerson and Amalai Oyaki, both engineers at NASA JPL. Next slide. So scientists around the world, we've had numerous issues with data collection and, well, in remote locations, and that includes NASA, and even in the outstanding research projects we just heard about, which utilizes various telescopes and spacecrafts. So in previous missions, NASA has used what is known as direct or single relay links, which is basically a point-to-point data communication system as pictured in the top right. However, with the complexity of more recent missions, as you may have heard, maybe Mars 2020, it proves that the solar system internet, it was developed for data communication involving relay nodes or spacecraft, which would be utilized for missions in deep space. So the solar system internet is based around DTN, or the delay disruption tolerant network. And unlike the internet, it does not discard data packets if there's a disconnection, but guarantees delivery by using the store and forward mechanism, which allows the data bundle to be stored in an intermediate node until the communication path is open for transfer. And DTN is pictured in the lower right corner. Next slide. So the objectives of this study is to demonstrate a solution to the data collection problem using the DTN protocols, and as well as a network of sensors to forward messages between nodes, along with the AIT, or the AMMOS instrument toolkit, which is used to control and manage the network, particularly in isolation or in remote locations, such as space. Next slide. So we hypothesized that using AIT, or the AMMOS toolkit, and the protocols for DTN ion, it would demonstrate and execute the forward mechanism between the nodes in the network, thus replicating the solar system internet using the delay disruption tolerant network. Next slide. So the methods of the study. So using the DTN protocols listed on this slide, the JPL implementation used Raspberry Pis that were programmed using DTN. And on those Raspberry Pis, it was a long range or LoRa radio hat, which was used to transmit the data between each node. And I believe it was about 951 megahertz. We opted to use both TCP or the transmission control protocol and the UDP, which is the user datagram protocol test applications, which are both network protocols for data transfer over the internet. So these test applications were written in both C and Python to send and receive the data, which was then chunked into data arrays. Next slide. And this is basically what the protocol stack with each layer looks like. So you have the test application that we created, and then it would be, I guess, passed into each layer. So there's a message layer, convergence, link service, and then the link between, which would then transfer each application to and from each other. Next slide, please. So the results of the study. So after doing the sample tests of the implementation, it was executed successfully in a controlled environment, which should be shown in the next slide. But the TCP and the UDP client and server applications for both the message and the convergence layer were successfully executed and were then modified for the nodes in the sensor network that we built. So when tested in the field, the network successfully transmitted messages on a dual channel, which was about 70 to 80 meters away from each individual node. However, in this research study, that distance didn't seem adequate enough. So what we decided to do was build a monopole ground antenna for each node. And because of this, it increased the distance between each individual node to about 600 to 700 meters, which is roughly half a mile. So once with this increase in distance, after testing, one of the nodes actually lost power during the small scale test, but which in turn experienced packet loss. But due to the store and forward mechanism, which is built into DTN, it was able to continue sending the same data packet until it was successfully received on another one of the nodes in the network itself, thus guaranteeing that there was no data loss, even though it experienced packet loss from the beginning. It was able to, I guess, remember the data packet that was being sent. Next slide, please. So this is, I guess, a schematic of the control network that we used for the first test that we did. So we had 3 nodes initially to begin with, and afterwards we increased it to, I believe it was 5 nodes, which we used, but in the field we kept it to 3 before we increased it to 5 as well. Next slide. So to conclude, the small sensor network that we built, it proved that the store and forward mechanism built into the DTN protocol was able to perform the task and get packets to its destination despite experiencing disruption. So this demonstrated the reliability of the disruption tolerant network in the solar system internet versus standard internet protocols. So this is important to prove the reliability because having a guaranteed data communication system will be crucial for upcoming deep space missions when transmitting important information from the spacecraft to Earth. Next slide, please. So here's a, I guess, a diagram of or a comparison between standard internet protocols versus DTN. So as you can see in the upper half, which demonstrates the standard internet protocols, it has to wait for a complete path before it can complete a successful data transfer. But in the lower half, it shows that DTN can make, I guess you could say, incremental progress between each link without a complete end-to-end path. So, and in turn, it would take significantly less time to transfer data, which proves the reliability of DTN. And also, you know, the time it takes to transfer data, you can send numerous packets between the spacecraft and Earth versus using regular standard internet protocols. So next slide. So in the future, we plan to increase the number of nodes from 3 to 5 to hopefully 10. to create a larger network to conduct a larger scale test across a bigger plane. This will test the network's range, the reliability, and the redundancy, as well as flexible data transfer as proved in the small scale test. Also, we hope to apply this, data communication network system to UVI's own CubeSat for its own data transmission purposes as well. And the next slide, it would be just my acknowledgements and contact information. So that concludes my presentation.
Thank you very much, Stephanie. Very nice presentation. We have a couple of minutes for a question.
Hi, this is Professor Kentop. This is really fascinating stuff, and I was wondering, do you know which version of the IP protocol was used for the trials? Was it version 4, the legacy version of IP, or was it the new IPv6?
Oh, it was version 4 at the time, because this project has been going on for a few years now. So at the time of using the internet protocols, it was version 4, the legacy.
It would be interesting to see if there are any differences with the new version of IP, because there's better fault tolerance, error correction, and security built in. So.
Oh yes, for sure. I actually have been discussing that with my mentors. They were planning to, redo that test again and use the newer IP protocols to see the differences between the first one with version 4 versus version 6.
Fascinating. Thank you.
No problem.
Thank you again, Stephanie. Very nice presentation.
Thank you.
And our second to last speaker of the day is Javier Galiber. I apologize if I mispronounce your name. So we can.
No, it's okay.
Can pull up the slides. All right, so I guess you submitted a pre-recorded presentation, is that correct?
Yes, that is correct.
So I guess we'll listen to that and then you'll take questions afterwards.
So just for a quick introduction, Javier Galiber is with the Applied Mathematics program, and he worked with us in cybersecurity for his ECS summer research.
I guess we can start. I cannot hear anything. I guess, Tim, your mic is muted. So probably you should unmute yourself so we can hear.
I think you have to share your audio from your computer.
Yeah.
It should be shared. It should be live. The audio is up this way and up this way. Let's try this again. Please stand by.
Hello, my name is Javier Galiber, and today I'm going to be doing a presentation.
Is that better?
Yes, we heard it.
Okay,
yes.
Good. All right, thank you.
On the detection, assessment, and mitigation of public network exposures in the U.S. Virgin Islands. Our preliminary investigation started with an assessment of the public network exposures here in the territory, along with a look into the firewall integrity and availability across multiple devices on a given network, and to see if internet service providers have adopted Internet Protocol version 6 here in the Virgin Islands. For our research question, I wanted to see if we can use different protocol versions on the same network to improve local network security. So the first thing that was conducted was some background research on networking and how cybersecurity works, as well as the use and interpretation of GRC shields up and to understand Nmap's features and application. I also conducted several trials on business and residential networks. I also conducted further background research to determine if ISPs support IPv6 here in the US Virgin Islands. I also wanted to validate if wireless access points or routers also use IPv6. I also wanted to verify if the test devices could be configured in IP6 only or IPv4 only modes. Moving on to network exposure methods, I used GRC Shields Up to test firewall integrities while using Nmap in tandem to discover exposed hosts on public networks from a pool of 900,000 addresses. Moving on to trial procedures, the first thing I had to do for my research question was reset the modem provided by the ISP, reset the consumer wireless access point or router, and connect/verify each test device to make sure that they're connected, and attempt network interactions for same and different hosts. And lastly, this test was repeated 3 separate times. Moving on to the GRC firewall assessments. This is the results from my firewall testing that I did earlier in this research program. The firewall protected service, a firewall protected network that is being shown in all green, means that a hacker cannot see whether a port is open or closed and cannot perform any malicious attacks to the network. While a total exposure, on the other hand, is represented by this all blue, and that means that a hacker can see whether or not your ports are open or closed. In this case, they are all closed. Now, if it was all open, all of those blue dots would be converted to a red color. And that means that a hacker can do a lot of malicious attacks to your network. Moving on to our network exposure results. For the residential side of things, out of a total of 8,500,000 total hosts, 70,000 of those were exposed to the internet. That means from the total, 8.28% of them were vulnerable to malicious attacks, while on the business side of things, 16,000 total hosts was used, and out of those total, 4,000 of those were exposed to the internet. That means that 25.6% of the business network is exposed to the internet. That means that the business network is 3 times more exposed than that of the residential network. Another important discovery was that the ISP service routers use default passwords that are documented and published on the internet. That means hackers can gain access and disable firewalls and other security settings on your home or business network. As for the research results, I found that the IPv4 can only communicate with like devices running IPv4, and the same goes for IPv6. It can only communicate with devices running IPv6. That means that they cannot communicate with each other, meaning that IPv4 cannot communicate with IPv6. And another discovery is that IPv6 is not supported by the ISP in the territory. Now, to show some examples of this happening, we have an IPv4 computer trying to communicate with another IPv4 computer and is able to do so, while the IPv6 computer is attempting to do the same thing, but is not able to since they are different IP versions. So to conclude some of this information, tens of thousands of exposed hosts found in the US Virgin Islands and Puerto Rico, along with server router defaults that could compromise networks. The hypothesis for my research question was proven true with the use of several different protocols, along with IPv6 not yet available or supported in the territory. To continue my investigations in the future, I would like to research the nature of network exposure here in the territory, along with testing my hypothesis for my research question with other ISPs and mobile hotspots, along with investigating transition protocols that allow IPv6 to work on IPv4 networks. And lastly, I would like to pay special acknowledgements towards my grant and my mentor, Professor Timothy Kentop. And here are all the references that I have used. Thank you for having me. Does anyone have any questions? Hello, my name is Javier.
Thank you for your contribution, Javier. Very interesting. We have time for a question. If there are no questions, then I have a very naive one from someone who is not very much in the field. Can you please summarize in a few words what the main differences between IPv4 and IPv6 are?
To summarize, IPv4 is a version that was created back when the internet was in its early stages, and it was used as a sort of address similar to home addresses. But after a while, the amount of available IPv4 addresses were starting to shorten out, and thus IPv6 was created to rectify that problem.
This is Professor Kentop. More specifically, IPv6 includes 4 times the number of binary bits in the address space. So it is exponentially larger. There should be enough IP addresses to cover 1 million devices in a square meter on the surface of the Earth, basically. So it should solve the shortage problem quite nicely.
Okay. Thank you. So the last speaker for this session is Darren Paul, who actually asked me to share his screen for the presentation. So Darren, you can share your screen.
Okay. Can you guys see my screen?
Yes, we do.
Okay.
So Darren did his summer work at the University of the Virgin Islands Observatory, working with Dr. Bryce Orange and Miss Priya Gokuldas. And Darren, you have the floor. Go ahead.
All right. Good afternoon. My name is Darren Paul, and I am an upcoming sophomore at the U.S. Virgin Islands, the UVI St. Thomas campus. My major is applied mathematics, the 3-2 program, and my mentors are Dr. Bryce Orange and Miss Priyadarshini Gokuldas. Okay, so the overview. So basically, this presentation will contain the following: the introduction, the various images that the Virgin Islands Robotic Telescope takes, which includes bias images, dark images, flat images, and science images, and then a flowchart of the pipeline, which essentially processes these images so that it can be further utilized. So the purpose of my project is to study the pipeline, which is a series of data processing entities linked in a series of the Virgin Islands Robotic Telescope located at the Ethelman Observatory. It is crucial to understand the various types of images that the telescope produces, which includes bias images, dark images, flat images, and sans images. So first up, we have bias images. Bias images, or sometimes bias frames, as people call them, are a series of images with zero exposure time, meaning with the shutter closed. Because of this, they lack photoelectrons as well as thermally excited electrons. Photoelectrons are essentially electrons emitted when electromagnetic energy, which is light, makes contact with any material or surface. And thermally excited electrons are essentially electrons excited by thermal energy or heat energy, which allows the electron to jump to a next higher orbital. The bias images, the exposure is about 10 seconds, and the reason it's very short is to prevent noises from keeping in. Noises can be defined as any random factor that could pollute the image and basically give inaccurate data. So next up we have dark images. Unlike bias images, dark images are long exposures taken while the shutter is closed, just like bias images. And because of that, there are no photoelectrons. Dark images produce dark current, which is the thermal excitation of electrons, and it must be measured and removed from sans images, which are the final product. Dark frames are taken because dark current has to be measured and then removed from sans images, similar to a bias level. What an interesting fact is that photoelectrons in this case are indistinguishable from the thermally excited electrons. So next up we have flat images. Flat images are basically pictures, well, frames taken of the twilight sky, which is essentially the same or uniform throughout. What I mean by this is that the images don't have that much variation, little to no variation. And any variation in the images will be caused by vignetting, pixel to pixel variations, and dust grains. So vignetting is the reduction of brightness and saturation as a result of the lens's limited diameter, or simply because something is obstructing the light path. Pixel to pixel variation is basically just as the name suggests. Not every pixel is the same size, and because of this, some pixels will obtain more photons than others, and then dust grains sometimes end up on the lens and filters, which appear as small black circles, which you can see here under these two images. They can obstruct a portion of light that the lens should be receiving. There are also two types of flat images. There are dome flats and sky flats. Those I still have to work on. Flat images, just like sans images, which will be discussed in the next slide, are filter dependent, unlike bias images and dark images. So each filter has its own characteristics and according to its bandwidth. The Virgin Islands Robotic Telescope uses Johnson filters, and the bands that they have are B, V, R, and C. So sans images. These images are basically images taken of stars captured in the night sky. And in a sense, you can call sans images a compilation of biased, dark, and flat images, but only after they're processed accurately, and these images need to be free of any noises. So that is why um, it's a compilation after the images, the previously discussed images are processed. Just like flat images, sans images also use filters, and if sans images do not have the same filter as flat images, then it can cause the final image to possess excess data or miss some data entirely. So this is basically a flowchart of the pipeline. All images start out as raw, meaning that they're like freshly taken and they have noise in them. And then as the processes go along, the noises are removed from the images so that we can get an accurate image of the stars in the sky. To conclude, the pipeline is very important because the final image, the sans images, has to be free of any noises such as heat from the actual machine itself or humidity or dust, and it is needed to accurately measure the luminosity or the brightness of a star. The pipeline allows the images to be assorted, organized, and processed. And the purpose of my project was to create and maintain a report so that others could understand and carry out the processes of using the pipeline to reduce sans images. This is the end of my presentation. I would like to acknowledge my two mentors, Ms. Gokul Das and Dr. Bryce Orange, as well as Dr. David Morris and the rest of the physics departments. Is there any questions?
Thank you very, very much, Darren. You finished right on the 10 minutes mark. So since I guess this is the last presentation, I can, like, if there's one question, we can take it.
Can you go back to the slide number 8? Sorry. The diagrams of the processing.
Slide number 8?
Yep.
Oh, okay. Is this? Oh, my bad.
Oh, you're fine. Yep.
Can you see it?
Yeah, I can see it.
Yeah. This is basically the. Oh, my bad.
Yeah. So you take the medium dark image in the second raw, but you don't use it anywhere in the pipeline.
The medium dark?
Mm-hmm.
Oh, yeah, I do. Yeah, that was a mistake. You see right below the raw sans images, to obtain the image that we would use to obtain a master sans image, we formulated this equation where we would subtract the medium bias image. Okay, so RS minus MB minus MD divided by NF.
Right, so why you subtracted medium dark only from the science image and you do not subtract it from the medium bias or the normalized flat? Because the dark is under 9 every image we take, right?
Yeah.
So should the dark also be taken away from the biases and the flats?
Well, yes.
Yeah, that's right. That's the correct answer.
Yes, so MD here.
Right.
That would
So
represent median dark.
correct. So the dark should also, the median dark should also be subtracted from the bias and from the flat images before you do the median bias and the median flats.
Yes.
I think we want to be careful, Nino, though, on what terminology we're using, right? So if they mean if by bias, they're meaning, you know, a 0-second exposure, which is usually what we mean,
right?
Right? Then you want to go the other way, which I think Darren is doing, right? You definitely want to take the bias off of the dark, which I think he's showing in the second column there.
Correct.
Right? Draw dark minus the median bias.
Should be the other way around, right? Should be the bias.
No, I think he's got it right, because you want to take the, you know, basically the noise, the median bias.
Yes.
Is showing the electronic noise, right? So
right.
The bias is in the dark, but the dark is not in the bias, right?
Correct.
So I think that's okay. I think maybe the one thing that the thing that you're picking up on, you know, is that I don't see them doing a dark subtraction on the flats, right? But maybe it's not really critical because, as like you pointed out, when you had Megan, right, do the analysis on how much dark current we actually get, and it's not really a lot. If it's going to be long images, then, you know, I think it's important. But for something like a flat, which is 2 seconds or 4 seconds or something, probably doesn't really matter a whole lot.
Yeah.
Okay. I suggest that at this time we play Jordina Pierre's presentation with her voiceover. And we'll conclude with that.
There is also a question that was posted for Javier Galliper, and Mr. Galliper did not have the opportunity to answer a question, even though he had time left for a short Q&A. So he's going to respond to that in chat, and we'll start this other presentation. Just wanted everybody to be aware of that. Thank you.
Regarding that question, I was in contact with him and I answered the question for him. But if you want me to recite it, I can.
If you could just post the answer in chat so everybody could read it, that'd be great.
Okay.
Thank you so much. And, let's see. Almost there.
Hi, good afternoon. My name is Jordina Pierre, and this is my presentation on the work that I did this summer. It is a continuation of the work that I did last summer, and the title of my presentation is Simulations Through Megalith and GN4. So this project aims to develop a detailed radiation simulation that will inform design parameters for the UVI gamma ray experiment for astrophysical transient missions. And this will help to complement measurements of Goddard's CubeSat mission burst cube. This gamma ray detected instrument will focus on detecting sources like gamma ray bursts and other cosmological sources of gamma rays. And these gamma ray observations will help to better identify potential sources of gravitational waves by pinning down the exact time of the event, and it will complement burst cube, which has some limited capability for event localization. The image that I have in the background is a picture of a neutron star merger, and I enter this image because neutron star mergers actually produce gamma ray bursts. So missions that already measure or plan to measure gamma ray bursts are Fermi, burst cube, and UVI grid. Fermi, the Fermi Gamma Ray Space Telescope, or formerly known as GLASS, was launched in 2008, and they opened the door to the high energy exploration, and it helped answer a lot of questions about black holes, gamma ray bursts, and so much more. And so to complement Fermi, BurstCube, a 6-unit CubeSat, was designed to detect and localize gamma ray bursts with more of a focus on short gamma ray bursts, because there are two types of gamma ray bursts, long gamma ray bursts and short gamma ray bursts. But the problem with BurstCube is that it orbits the Earth, funny, and we want more coverage because let's say a gamma ray burst occurs in the western part or western hemisphere of the Earth, and BurstCube happens to be in the eastern hemisphere, then we've lost that data and we're not able to capture that because there is no instrument in that region. So this is where UVI grid will come in, and it will help to complement the measurements of BurstCube as well. UVI grid is a technology demonstration that will be used on HASP. HASP, short for High Altitude Student Platform, provides high altitude balloon flights for 12 student experiments at an altitude of about 36 kilometers over a period of 15 to 25 hours. And these flights are an excellent way to flight test compact satellites or prototypes or fly small experiments. So the operational concept of UVI grid. There are ways for the gamma rays to interact with the crystal when they are produced, and that is through Compton scattering and a photoelectric effect. When the photoelectric effect happens, a photon undergoes an interaction with an electron which is bound in an atom. In our case, the photon would be the gamma rays. If you're looking at the picture right here, the light gamma rays would be, well, the light rays would be our gamma rays. And it would interact with an electron inside of the scintillator crystal. And in this interaction, the incident photon would completely disappear, and an energetic photoelectron is ejected by the atom. And that is why you see electron emission. The electrons are coming out as photoelectrons. And if not the photoelectric effect, we have Compton scattering. And Compton scattering is the scattering of a photon by a charged particle, and it's usually an electron. And as you can see in the image that I have here, there's an X-ray photon, or in our case, a gamma ray photon, and it interacts with the electron, and now you have the photon scattering as well as the electron scattering. And when this happens, there's a decrease in energy of the photon, and it has a different energy than it did coming in. The energy has now decreased. Now we have the challenge, which was simulating UVI grid. And in order to do this, we had to start off with the Megalib, or we had to use the Megalib software. And Megalib stands for Medium Energy Gamma Ray Astronomy Library, and it represents the complete data analysis chain from simulations to high-level data analysis. It was originally developed for the Mega Gamma Ray Telescope. The source code is C++, and when I finished compiling it, it took about 4,556 seconds. This was outputted by the program itself in the terminal, and this is equal to about 75 minutes and 36 seconds, I believe. And when this was done, there were user-friendly GUIs, and it enabled the user, me, to run different simulations depending on what I needed or what I inputted. And this image that I have here, I have a breakdown of the Megalib software, and I circled software applications that I personally use for this research. GN4, which is also known as Cosima, was used, as well as Revon, which I will explain further in the presentation. So now we have preparing / running GeoMega. GeoMega is responsible for building up the active volume that we want to simulate. It's a detector package in Megalib, and it was used in this project to actually create the simulation model of the scintillator crystal. As you can see here in the bottom left corner, I have a GUI of the GeoMega. When you actually enter the command in the terminal, this is the GUI that pops up. And in order to actually run GeoMega at that geo.setup file, was first created because it's a prerequisite, it must be done. The name of my .geo.setup file was geomega_version1, as you can see in the picture on the right with the code. And the information, this file held all the information needed to actually create the geometry shape, and it allowed the user, me, to define other properties such as rotation, position, and energy resolution. Here is the result of my geomega file. When I actually ran it, this is what was produced. If you actually did have this file on your laptop and you run it, you'd be rotated as much as you defined it in the file. And these green arrows that I drew are my beams that will be shot at my crystal model. In the right corner here, you can actually see what was outputted by the program, and it tells you how long each stage took to complete. Next, we have GANT4, also known as COSIMA, and this application was used to simulate the high energy gamma ray particles that will be shot at the simulation model. A source file for the radioactive element was also created to simulate the high energy particles, and it was combined with the geomega file in Revon, which I will explain in the next file. And Revon is short for Real Event Analyzer, and it would take the simulation data and provide physics quantities that can be compared with observations. I have a picture attached here of my .source file. So Revon and results. In the background, you would actually see the GUI of the GUI that popped up for Revon. And when we combined the geomega file and the COSIMA file, this picture in the left corner is what was produced. I labeled it Revon Bismuth 207 photoelectric peaks, and I compared it with readouts from the SIPAM for burst cube. And as you can see, they're pretty similar. So it goes to show that this is pretty accurate. It depends on what you input. And Revon is the analysis code that turns everything into meaningful analysis. And it's the actual simulation package. And the energies that were used for Bismuth 207 were 569.7 kiloelectric volts, which is where you could see the tallest peak, and 1063.66 kiloelectric volts, which you see as the smallest peak. And it matches pretty close to the readout from the SIPAM for burst cube. So for future work, I would like to be able to simulate other radioactive sources in the lab, like and cesium-137, and also be able to determine the energy resolution as a function of energy, which would have to match what's already been done in the lab. And I would also like to start simulating real sources like the Crab pulsar and evaluate the effective area of the instrument. Thank you so much. This is the end of my presentation.
All right. I don't think we should take questions without Jordina being here and able to answer. Or we can make sure we can ask her a question whenever we'll meet her around UVI, I guess. All right. Go ahead, Tim.
On behalf of the ECS Scholars Program and the University of the Virgin Islands and the National Science Foundation, we greatly appreciate your participation in our first ever virtual ECS Summer Symposium, and we look forward to our fall symposium ahead. And for those of you that have worked hard all summer long to learn and share, we appreciate all the love, the blood, sweat, and tears that you have put into your respective areas of research. And we look forward to seeing you again this fall. And at this point, I'll turn the mic over to Dr. Carbone to see if he has any closing remarks as well.
Well, I guess we can read the closing remarks that we got. Let me just open that up. So I guess I did not receive the official statement as for the beginning one. So I guess, Tim, if you have that to read, you can go ahead and do that. Otherwise, I can come up with some sentences myself. Well, we need to basically.
So, yeah,
Okay,
so basically, the email I received earlier had opening remarks, but I don't think there was anything in terms of closing remarks. So I can double check again, but.
Okay, so then we can just thank everybody once again. And I want to remind everyone that this session has been recorded, and that recording, a link to that recording, will be available on request. And finally, we want to acknowledge again the support from the National Science Foundation, HBCU UP grant, the NIH RISE, and the MARC grants, as well as the College of Science and Math and the Emerging Caribbean Scientists Program, and all the generous donations from private donors.
And NASA.
So
and
thanks.
NASA. We most of the presentations today, NASA. So
yes.
Anyway.
And also a big thank to everybody who participated in this program, and to all mentors and their commitment and support for contributing to the undergrad student success. Thank you, everybody, and we can close the meeting here. Thank you again.